I'm continuing from where we left off in the previous video, talking about how to prove this theorem. This is the next video in a short series on how to take your first proof-based math course. And in the previous video, we analyzed the logic of this statement. We did the proof of the only if direction, and now we're going to complete the proof of the if direction. Now, note that we assumed that n is some integer, and that is still in force. We completed the direction for the only if part of the statement. I won't write that out all over again, but we're moving on to the if component. So we want to assume for that, like doing the most natural, straightforward thing, this is the notion of direct proof, is that we would assume the antecedent of that conditional. Well, the antecedent of that conditional is that n squared is odd. We want to prove the consequent. That means we want to prove that n is odd. As I have emphasized in a previous video, when you do that, what you want to do is unpack definitions. Since we're assuming that n squared is odd, that must mean by definition that there exists an integer k such that n squared is equal to 2k plus 1. Notice that I don't need to worry about reusing the letter k because we kind of finished using it, right? It kind of like the lifespan of that variable, so to speak, ended when we ended the only if direction. So I'm free to reuse it. I mean, you could call it something else, but it's fine to call it k. From here, we know that we would like to learn something about n. We're trying to show that n is odd from this assumption. How do we do it? Well, if you think back to what we kind of correspondingly did in the other direction, we had n equal to 2k plus 1. And in order to work toward understanding n squared, we squared both sides of that equation. Could we do a corresponding thing here? If we have n squared, how do we get back to n? Could we square root both sides of this equation? Yes, you certainly could. But there is going to be a massive problem, which is that when you take the square root of this side, there is no nice simplification of that. You cannot distribute the square root to each part, and we don't have any notion of multiplying out, right? That's what we could actually do when we went from n to n squared. It was with the square, we could multiply out all the terms, and that gave us a way to make progress. Now, I'm always trying to take the things that we do in this particular proof and generalize them, relate them to proof strategies more generally. And here we seem to be stuck. And this time, I mean really stuck. There really isn't a good way forward from here. So what do we do? And again, connecting this to the general process of proof strategy, what do you do when you're stuck like this? Well, you can try to continue thinking about it, but in this particular case, it's probably not going to go anywhere. The right thing to do in this case, and in some other cases that you will encounter, is to change your proof strategy. Now, I have been emphasizing that whenever you have a particular logical structure, it tends to correspond to a standard method of proving something with that structure. And in the case of conditionals, that means direct proof, right? You have if p then q, that's your logical structure. The corresponding standard way to prove something like that is to assume p and then prove q. But I've also been giving this caveat that the most direct way doesn't always work, and we're seeing an example of that right now. Now, there may be many ways to alternately attempt to prove something, depending on what the logical structure is. For conditionals, one fairly common alternate way to prove a conditional is to use the contrapositive. So if p then q is equivalent logically to if not q, then not p. And that's what we're going to try to do here. So for us, the p in if p then q is the statement that n squared is odd. The q is that n is odd. Well, we are going to flip that around and negate each component. That's the contrapositive. That means we want to prove the statement that if n is not odd, then n squared is not odd. And notice, and we're going to take it for granted, right? In some classes, you might have to prove this, and in some, you can take it for granted. but we're going to take it for granted that if n is not odd, then it must be even. So in order to do this, we are going to assume that n is even, because that's the same thing as n not being odd, and that's what we want to assume right now. What we're trying to then prove on that assumption is that n squared is even. Of course, just like being odd has a definition, being even has a similar definition. Its definition is that there exists an integer k such that n is equal to 2k. Notice why this is such a better way of approaching the proof is we're back to being able to deal with n and work towards something that has to do with n squared, and we have good, useful algebraic rules that help us to do that. Again, as I try to relate these things to more general proof techniques, what I'm getting at is that sometimes when you start trying out a proof technique or a proof strategy, you can kind of tell in advance that it's going in a good direction. This already feels better than the earlier strategy did. Now, at this point, everything goes very similar to how it did in the other direction. So we square both sides to get something that's about n squared, and then we pull out a factor of 2. That satisfies the definition of n squared being even, and the proof is complete.